All right. Hello and welcome to my presentation to the hardware implant revolution. And today we're going to unveil ISM bands on hardware physical implants for red team operations. All right, we have the agenda for today's presentation. We will start with an introduction about myself and what I do in my day-to-day basis. We will continue with examples about of current physical implants and the advantages and disadvantages they have. And once we have identified the disadvantages and found the main communication challenge all of them have, we will establish a possible solution with a new physical implant design and the hardware and software implementation for it. We will continue with a couple of video demonstrations with the new design, and we will finish with some conclusions and further steps in the development of the new physical hardware implants. So a little bit about me. My name is Fernandez Minguillon, and I'm father of 3 children. I have 6 years of experience in offensive security, where the last 4 years has been a Senior Red Team Analyst at United Airlines. I perform and lead red team engagements, including network and physical assessments. And I also manage and triage the United Vulnerability Disclosure Program too. I'm currently pursuing my master's degree in cybersecurity, with the goal, of course, of trying to graduate this year. If you are interested also in my work, here is my LinkedIn and my Twitter profile, so where I post relevant cybersecurity material too. So let's get started. Like currently, in the customer market exists several physical implants that are being used in red team physical assessments, right? Such as the palm plug, that is the one that is in the top left corner, or the rubber ducky, or the bash bunny. All of them have a goal in common, right? And it's established a remote communication between the red team infrastructure and the physical implant by, for example, create a remote shell or exfiltrate credentials or recon the network for vulnerabilities. In almost all these situations, all these physical implants are deployed in places where the red team operator doesn't have a knowledge of the network. Or if there is an EDR, that is basically detecting commands that are being executed on a workstation. Other physical implants, for example, require to have an external connection through the internet, like a hotspot of 4G, right? But sometimes these 4G signals are not available, making the attack for this specific physical implant more or less useless. So understanding these disadvantages, the main problem I identified is that the current physical implants rely on, what I identified is that the current physical implants lack on reliable remote communication to the red team infrastructure. So, therefore, here is our goal. Our goal is to implement and develop an alternative long-range method of remote communication for our red team operations where the traditional internet network is not available. So the solution that I found is by using the application of packet radio and the LoRa modulation. But what is packet radio? Just like a concise idea. Packet radio is the application of grouping data into packets that are transmitted via a radio communication link. This grouping data into packets is made by a terminal node controller that implements the KISS protocol. And what is LoRa? Well, LoRa is a physical radio communication technique based on the spread spectrum modulation. The reason behind the election of LoRa for this project was due to their benefits in long-range connectivity and wide coverage, including in urban areas where we do perform red team operations. Also, there is a low power consumption and the efficient data transfer, making it ideal for applications that require transmission of a small data package. So how these two things, these two concepts come together? Well, with the LoRa C2 framework. The LoRa C2 framework is a compendium of hardware and software tools that I developed, and allow us to establish a long command and control communication between two or more nodes by using, again, the technology of packet radio and the LoRa modulation. These tools are the following: the LoRa C2 hardware module, the LoRa terminal node controller, and the LoRa command and control, or LoRa C2. These three tools are embedded together in the following hardware implant that we see in the picture. The new physical implant design is made of Raspberry Pi and a URT LoRa module attached to it. The URT LoRa module oversees the reception, transmission, and transfer the radio signals to let the Raspberry Pi understand those zeros and ones sent over the air. The reason behind the use of physical implants such as Raspberry Pi based on microprocessors is because they are more flexible to use in unknown environments because the operator has more available tools to use. Therefore, has more options to on the type of attacks to perform, such as wireless attacks, network attacks, or any other radio frequency attacks. On the other hand, the use of physical implants based on microcontrollers are limited in the type of actions or attacks these can execute, limiting them to one or two types of attacks. In the next slide, I will cover in detail the software and hardware implementation on the new hardware physical implant design. The hardware and software implementation here for the LoRa C2 framework is shown in the diagram attached. So in the hardware side, the LoRa hardware module is designed with eByte E22 URT LoRa module. In the interior of this module resides a transceiver, the LLC68, and a Texas Instrument microcontroller. This microcontroller is in charge of setting up the LoRa variables, the LoRa modulation variables, such as the spreading factor, frequency, and bandwidth. The microcontroller also acts actually as a bridge to converting the SPI bus on URT communication. In the other part of the hardware, in this case, like the Raspberry Pi, has the following software implementation. We start with the terminal node controller that I denominated LoRa TNC. LoRa TNC is a modified version of an open source project called TNC Attached, developed by Mark Kivist, and is written in C, and basically is in charge of converting the URT LoRa module on a LoRa network interface and translate the serial communication coming from the LoRa module in point-to-point communication. This is basically the core of the packet radio. We will continue with the network manager that has the goal of creating the TCP layer using the point-to-point protocol established in the LoRa TNC interface. And the reason why I choose the point-to-point layer 2 protocol is because there's only 4 bytes required on each LoRa packet to establish a link between nodes. Another alternative will be using the Ethernet protocol in layer 2, but in this case requires 18 bytes instead of 4. One reminder about this type of technology is that LoRa, the LoRa modulation has a maximum packet size of 240 bytes, meaning that if we use more bytes for protocols, less packets we have to transmit data. The physical implant command and control also comes hand in hand with what I call the LoRa C2. At this time, are only 2 bash scripts, server and implant, but soon I will release a new C2 application also developed in Python. The server bash script is acting as a listener, and when the implant script is executed, a reverse shell is generated. The reverse shell is generated using OpenSSL with symmetric encryption, satisfying the encrypted communication between the physical implant and the LoRa C2 server. And to finish, with the software implementation, the physical implant and the LoRa C2 server have several services that are executed on boot. These services allows to execute the LoRa TNC application and the network manager IP configurations on boot. Additionally, for the physical implant in particular, the implant script is also executed on boot with the goal of making an easy deployment in the in-field operations. So after the explanation of all of this, this is the OSI model or network stack that we're going to follow. In the layer 1, we will have the physical layer, in this case, the LoRa modulation. In the layer 2, the data link layer is done using the point-to-point protocol handled by the terminal node controller. In the layer 3, the network layer, we have IPv4, UDP, or ICMP protocols in charge by the network manager. And to finalize, in the layer 7, the application layer will consist on the SSL TLS protocol that encrypts the data in transit. As a recap, the show diagram explains the LoRa C2 framework structure for our red team operations. In the left side, we have the LoRa C2 physical implant with the implementation described in the LoRa C2 framework. And the LoRa C2 hardware module with the combination of LoRa TNC application and LoRa C2 implant script, communicating with the LoRa C2 server in the right side with the same LoRa framework implementation. But in this case, executing the LoRa C2 server script instead of the implant script. This sounds a little bit confusing, I know, but in the next slide, I will demonstrate how the communication is applied in this infrastructure. So in the following video, I will show the operating system services and configurations of the LoRa TNC application and the network manager. Additionally, I will demonstrate the communication between the physical implant and the server using the ICMP protocol. All right, so as you can see here, the screen is divided in two parts. The superior part, we have two terminals. The left one is the LoRa C2 server terminal, while the right one is the physical implant terminal. Both are for the testing purposes as an SSH connections. And in the inferior part, we have the SDR++ application set up to the LoRa frequency that the server and implant are going to use in order to identify the radio frequency signals. So in the first step, in the LoRa C2 server, I'm showing the LoRa TNC service and how it's executed. We will continue with the network manager service that configures the LoRa interface and put in a static IP address of 192.168.16.1 on a point-to-point communication. And we finalize by checking that the IP configurations on the LoRa interface are properly established. Now on the physical implant side, you can observe the same LoRa TNC service as shown in the previous terminal. And we will follow with also the network manager service that configures the LoRa interface to the static IP address of 192.168.6.2 on the point-to-point communication. We ended also by checking again the IP configurations on the LoRa interface and are properly established, creating a point-to-point communication between the implant and the server. And to finalize the demo, I will demonstrate the communication, as you can see there, by sending ICMP package between the server and the implant, as you can see right there in the SDR++. So when I was performing also this ICMP testing, I also did an extra test to understand the range communication between the physical implant and the LoRa C2 server. In this new test, the implant was deployed inside of a building, and the operator started to send ICMP package from the LoRa C2 server while I was walking on the street. The testing specifications were the following too. The power of both transceivers were 22 dBi or half a watt with no antenna gain. And the frequency was like the ISM band for the United States, 913 megahertz, with a data rate of 62.5 kilobits per second. This corresponds with 500 kilohertz of bandwidth and a spreading factor of 12. The conclusion achieved was that the maximum communication range was 260 feet, as shown in the map attached. So continuing with more demonstration in this one, I will cover the command and control communication between the LoRa C2 implant and the LoRa C2 server. But before of this, I'm showing you the attack architecture that we're going to follow here to let you understand a little bit better. The attack architecture is the path that the red team operator is going to follow to compromise a vulnerable machine that is located on the network that we are attacking. In this case, is the blue box, right? So to give you a little bit of context, the red boxes are those machines that the red team operator or the red team handles, while the blue ones are the victim networking machine. First, the red team operation is going to connect to the LoRa C2 server, like before with over SSH, and execute the LoRa C2 server script, and waits for the LoRa C2 physical implant to start the communication. The LoRa C2 physical implant then is deployed in the victim network by, for example, like connecting it to an empty Ethernet socket. When this, the C2 communication is available, the operator can start doing the recon on the victim network and find a vulnerable machine to exploit. So in this case, we're going to begin by showing the code of the LoRa C2 server script. And this script listens on any host on the port 4242 using OpenSSL with symmetric encryption. Next, what we're going to do is execute the script. At this point, what we're doing is waiting for the operator to deploy the physical implant and have sending the initial TCP packet to establish the OpenSSL communication. So if we see in the SDR++, we're going to see it soon, that communication that is starting. There we go. Once this communication is established, you can see the reverse shell on the physical implant as shown using the uname command. Following with demo, I will be showing the implant script. In this case, the script variable, air host, rport, and PSK keys are the same that we saw in the server side too. And the next we see is the service that is going to be associated with this script that is going to be executed on boot too. In this case, the service is executed every 10 seconds, so we know that is a reliable communication if we don't have that prior communication with the server. Following, what we're going to do is a quick recon on the victim network, and we're going to do an nmap scan on the port 514. As we can observe, the port 514 is open, running the shell service. By using the tool of RSH, will allow us unauthenticated users to reverse shell on the victim machine. Now we have a shell on a victim machine, as shown using the uname command. And to finish understanding the exploitation of this vulnerability or misconfiguration, we can read that the host EXIF file displaying us that allowing us any user on the network to use this service. So as part of the conclusions, we have these ones. It's easy to automate attacks and deploy it in the field. It's an excellent alternative as command and control for evasion and exfiltration during red team operations. The standardization of LoRa packets length of 240 bytes is not a limit factor to have interactive terminals as demonstrated in the field test demo. The low power and consumption allow us the physical implants also to run with batteries. And the system allows also a long range and high bitrate communication using low transmission and reception power modules too. The communication is in transit is encrypted using TLS PSK symmetric encryption. And my favorite part of this is that it's scalable, allowing the framework to use other digital modulations or higher power transceivers. And finally, it's cheap. Every LoRa C2 hardware module, once manufactured, will be cost between $30 and $50. As further steps for the development of the framework, we have these ones. Development of a LoRa C2 application to improve capabilities of reverse shell use, such as upload or download files, or the automation of binary generation for the implants. This is currently in the development phase. Development of extra long-range LoRa C2 USB adapter using a more powerful transceivers, like 1 watt or 2 watts. And I'm currently designing this right now. We continue with the implementation of a LoRa relay system to enhance the range of communication, currently also in testing. So the idea of this is like we can put the modules in different in different parts of the building, so we can communicate from outside of the building too. The development of a web-based LoRa configuration tool as an automated LoRa modulation variable setup script that setups the LoRa variables on the hardware module based on the LoRa server geolocation. This is basically, imagine that my range is too long, so the application is going to automatically detect how far I am, so I can reduce bitrate or reduce bandwidth to reach out to that LoRa server. And finally, design and manufacture LoRa C2 hardware modules for different physical implants form factors, such as Raspberry Pi Zero or any Redaxa mini PC, or in this case, the one that we're using at United, the Mili PCs. So to finalize, I would like to thank the organization for accepting this proposal of talk, and let me have the opportunity to present this research too. I want to thank you also, the United Airlines team, Red Team, for all the awesome engagement that we are involved in, that are the reasons why this research actually exists. And finally, to the DC414, that is the group of Milwaukee hackers that meets every first Friday of the month and demonstrate also that other type of hacking and knowledge sharing is possible due to their open-minded and relaxed culture in their social events. And thank you very much for coming to the presentation, and I will be very happy to answer any questions that you may have. Go ahead.
So did you consider any other alternate ways of doing this besides LoRa, and like what made you decide on this particular methodology?
So she asked if, can you repeat that again? Sorry.
Alternate ways, like what made you decide LoRa as the alternate C2?
So I choose LoRa because of the long-range communication. Also, is kind of trendy now. There is other options like GFSK and other type of modulations that has been in the market also around too. But also, there is a lot of documentation on the internet, and the LoRa Alliance has behind Semtech, that is a big manufacturer chip company that provides a lot of documentation. So it was easy to go through that kind of modules to expedite the realization of this kind of project too. Yeah, go ahead. So I didn't do any testing on the batteries, but I can tell you that every time that the module is transmitted, it only consumes 600 milliamps for every message that you send. So, and for reception, I believe is 40 milliamps. So the testing that I was doing were connected over like the electrical grid, so I didn't have that information yet.
Have you considered other projects like Mesh-tastic that sort of have the whole pipeline built out?
Yeah, I know Metastic, yes. I didn't go through that particular project in deep, but the idea of building this was like, I wanted to build something that I could handle in the lower layers of the network stack. Right? I wanted to build my own, basically my full network stack using LoRa modulation. And I know that Metastic can use like to text messages using microcontrollers too, but I didn't look that idea. But it's a good project. I heard about it. Yeah. Yeah. What's the question? So, can you repeat the question?
Yeah, how do you make sure that your LoRaWAN communication is actually encrypted? Are there good sniffers,
So this is not LoRa 1. So there are a lot of people already asked me about this. This is not LoRa 1 because LoRa 1 actually involves the layer number 2 of the network stack. While I use only LoRa as the physical layer, right? So when I actually capture the traffic with a TCP dump, like between both nodes. And you can see that is like, my idea when I implement the TLS or OpenSSL was to just encrypt the TCP packages that are being sent with the TNC, right? But no, it's not. I tried to avoid LoRa 1 because I didn't want to rely on their infrastructure. I was like, this is something that in red team operations we need to understand that the data or the traffic that we're going to send between our machines are only in-house and not relying on any other ones. Go ahead.
To expand on that, LoRaWAN and LoRa AC2, is that similar, like the same hardware?
I know, yes, I know that the same hardware can be used in LoRa 1 too. I'm not familiar with what kind of changes you can do, but I know that these particular modules, you can implement a microcontroller and with the code enter in the LoRa 1 infrastructure too. All right, well, thank you very much.